I guess we'll get started. So I plan to do the first 3 pages of the homework, and that'll give us 2 pages for next time. So that should be plenty. So for today, we have to talk, or yeah, we have to talk about the first derivative test and the second derivative test, and what these tests, what they give us or what they're all about. So these tests tell you information about critical points of your function, and basically they tell whether that critical point is a local min or max. So I think the way I'll do this is to basically recap the slides. So first, we need to recall what is the exact definition of a critical number. So he calls these critical numbers. They're also referred to as critical points or critical values. But yeah, a critical number is um, a value for x that makes the derivative equal 0 or makes the derivative undefined. So either of these two situations can, if either of these two situations holds true, then the value that you're looking at is a critical value, critical number. So, but usually the way that we encapsulate this is like, we think of this as a process. We take the first derivative of the function, we then set equal to 0 and solve, and that gives us the critical values, or at least it gives us most of them. So usually the critical values, critical numbers, they come from setting it equal to 0. But occasionally we also need to look at when is that derivative function undefined, and we need to then maybe pull those numbers in as well. Then with the whole collection of critical numbers, we end up drawing a number line using them. And that leads us to, maybe I'll write these. Maybe I'll write those down. So the critical numbers would then lead us to drawing a sign chart, which then leads us to the first derivative test. Okay, so the critical numbers are the dividers for the sign chart, and you'll see what I mean by that when we start working through some problems. But so we have the sign chart, and then we just read off. We look at the signs on the intervals, and that'll tell us the whether the thing is local min or max. So now let's look at the first derivative test and second derivative test in a bit more, I guess, I wouldn't say detail. Like, the slides are pretty detailed, but they're maybe a bit too detailed. So let's maybe just have a, this is how I think about the derivative tests. So the first derivative test is all about the transition of the sign. Like, how does the sign change from one side of the critical point to the other side? If it's going from plus to minus, then this is a local max. If it's going from minus to plus, this is a local min. And the way I think about it is I sort of visually sketch it in my head, like going from plus to minus. So plus, a derivative being positive means it's increasing. Derivative being negative means it's decreasing. And so then you just sort of like sketch these little things that tell you what it looks like approximately. Make that a little bit better. So with those little sketches, you can easily see like this guy should be a local max, this guy should be a local min. Okay, so that's first derivative test. Second derivative test. Well, when you read the statement, like on the slides, for example, when you read the statement carefully, it starts with a condition. It starts with a condition that your critical number that you're looking at is coming from the setting, the first derivative equal to 0 in solving. Like it has to be coming from this guy, not the other guy. The derivative can't be undefined there. Yeah, and that is an important condition. So for a critical number, I used A the last time. Maybe I'll use N this time. For a critical number N, with f prime of n equals 0, what you do is then the second derivative test is all about taking that critical number and plugging it into the second derivative. So yeah, we plug into the second derivative, and if it's positive, it tells us something. If it's negative, it tells us something else. And if it is equal to 0, then it tells us nothing. The test is inconclusive. But usually you won't see that. Usually it's got to be plus or minus. Okay. All right. So the way that I think about this is I use the fact that second derivative is concavity. So it being positive means that you have something that is concave up, which looks like this. If you have something that is negative, it means concave down, which looks like that. And that's how you tell that this guy should be a local min, and this guy is a local max. So really, really the test is saying if you have this condition, you end up with this conclusion. If you have this condition, you end up with this conclusion. The thinking about concavity is just the intermediary to let you like understand like, oh, this is how those ideas are grouped together. Yeah. What else do I want to say? So you keep in mind, like you should try to make these two tests like make sense. Well, what I'm trying to tell you about the two tests is they're telling you the same information, but you're doing slightly different things. Okay. The first derivative test uses the first derivative, the second derivative test uses the second derivative, but they use them in different ways, right? With the first derivative test, we take our critical numbers and we plug in values around the critical numbers and we look at how the sign changes. That's the first derivative test. Second derivative test, we take our critical numbers and we plug them directly into the second derivative. There's a distinction there, so keep that in mind. But both tests are giving us the same information, or at least they should give us the same information. They tell us for a particular critical number, they tell us, is that critical number corresponding to a local min or to a local max, or possibly to neither. So I told you not what neither would look like in the case of the second derivative test. In the first derivative test, it would just be if it's like a plus to a plus or a minus to a minus. So yeah, you can also have critical numbers that don't correspond to mins or maxes. But yeah, usually this is what you get. And so both tests basically are to obtain the same kind of information. And we'll see that for one of the problems that we do today, 6D basically, it asks us like which test do we prefer. And I'll say that usually we prefer the first derivative test because usually it's a bother to calculate the second derivative. But there are occasions where the second derivative is actually very easy to calculate, and so in those cases maybe you can prefer the second derivative test, but almost always I would say like first derivative test is usually the way you would go for. Okay. Any questions on this material before we get started? No. Okay. Right then. Let's crack through the problems. So, for number one, we have some profit function, and we want to know when is this function increasing or decreasing. So increasing, decreasing, you should immediately think about taking the first derivative because the first derivative will tell you that kind of information. So we go ahead and we take the first derivative, minus 200x plus 10200. And we would set this guy equal to 0 because we're going to set up the sign chart. Okay, so when we set this equal to 0, we're going to get 10200 equals 200x. We can then cancel off some zeros, and then we can divide by 2, so we get 51. Okay, so now when I draw a sign chart, a sign chart is a number line, but with some divisions in the number line. And I usually label my sign chart with the function that I'm looking at. So this is the sign chart for p prime. And the divisions correspond to when is this function equaling 0. So or undefined as well, because the idea is that the tick marks should correspond to places that divide up the number line into regions that are always like the regions should be all positive or all negative. And so you want the tick marks to be these separators for these regions that are all the same sign. Okay, so this region is all one sign, this region is all some other sign. It doesn't have to be some other, just a sign. Okay. And now we just look at the function and we think about what the signs actually are. So usually people will say like to like pick values and to calculate the actual number and then to look at like is it plus or minus. But really, if you can avoid picking an actual value and plugging in, that would be the best thing to do. It's faster if you try to reason about it a bit more abstractly. So for instance here, what I would do for this is I have to switch my thing manually. Okay, so like in this, so if we're greater than 51, what that's going to do is that's going to make this guy greater. It's going to make this term greater. So it's going to make the negatives dominate, right? Because at 51 exactly, we have the whole thing equals 0. We have this guy is equal to this guy. If we make it greater, then the negatives will dominate. If we make it less, then the positive is going to dominate. So you can pretty quickly get that without picking numbers. Although, I mean, yeah, we'll see one problem where you kind of have to pick numbers in our homework, but yeah, I try to avoid that if I ever can. Okay. Right. So with the sign chart now, we can then conclude the increasing and decreasing parts. So positive derivative is increasing. So that means it's increasing from minus infinity to 51, and it's decreasing from 51 to infinity. I was gonna say something about like this being like a bit unrealistic because obviously like in this problem, you're not gonna sell things for a negative quantity, but I'm just not gonna care about that. All right, and then the last thing that the problem wants us to do is it wants us to say something about like how much to charge, I guess, to maximize total profit. So well, according to this, you should charge $51 per pair. Can't spell. All right. Any questions on that? No. Okay. Number 2 is pretty similar. So starting off, we take the derivative of this q function. My stylus is not working very well today. I don't know why. Makes me switch everything manually. 110x to the 10 minus 110x to the 9, which we would set equal to 0. So what I will do is I'll factor this guy. That way I make sure I'm not losing track of anything. It should be 110. X to the 9, x minus 1. Okay, and so that gives me x can be equal to 0 or can be equal to 1. Okay. So these are the critical numbers. Maybe I should box those. When is Q increasing and decreasing? So once we have that kind of a question, I start by drawing a number line. Okay. All right. So this is where now I try to explain a different technique of how do you quickly fill in a sign chart when you have a factored form of your function. Because when you have a factored version of your function, it's actually very easy to populate the whole sign chart. What you do is you start on the rightmost side, and then you move left. So the reason is because when you start on the rightmost end over here with greater than 1, pretty much always like all the terms are going to be positive. You kind of maybe sometimes you need to check that but you can check very quickly like yeah, everything is going to be positive here. This x to the 9th is going to be positive. The x minus 1 is going to be positive. And so it's very quick to check like is the whole function q prime, is it going to be positive or negative? In this case, it's going to be positive. Okay. And then we jump over each of these divisions. And with each of these divisions, when we jump over, only one factor is going to be changed in sign. So going from greater than 1 to less than 1, this factor, x minus 1, will flip in sign. It'll go from positive to negative. Jumping from this region between 0 and 1 to less than 0, only the x to the 9th is going to change in sign. Only the x is going to change technically. Okay, so when you think about it this way, you end up realizing that what you need to look at is only, first of all, is only one factor, and secondly, the thing that is going to matter is actually the power that that factor is raised to. So, for example, if this x minus 1 was raised to an even power, flipping this over, yes, the x minus 1 quantity inside would go from plus to minus, but it then being raised to an even power would cancel the negative sign that would show up. It would end up not changing the overall sign of q prime, of the whole function q prime. And so, yeah, whether or not jumping over the sign actually changes the sign of the whole function is only going to depend on the power of the factor. So in this case, like you can fill these out pretty much immediately, just because both of these powers are odd. So because the powers are odd, you know that the sign is going to flip. It's always hard to like explain this technique to people because I don't know, it takes students a while to figure it out, I guess. But you can try to play around maybe, and you'll see that like this kind of makes sense. All you need to do is just like take a rational function in factored form and create such a sign chart and try to populate it, and you'll see that like it is all about the powers. If you really aren't comfortable with this though, like you can always resort to the picking a number and plugging it in. It's just that process is going to be a little bit slow. Okay. Yeah. But so yeah, we have a sign chart now. So now we can just read off the information about whether Q is increasing or decreasing. So increasing and decreasing. Oh, I can't spell. So increasing is going to be from minus infinity to 0, and also from 1 to infinity. Decreasing is going to be from 0 to 1. Right. And first derivative test. So yeah, that's just reading the information off of this. So I may as well draw a sketch on top of this graph. So increasing, decreasing, increasing. It'll look kind of like that. And so the local min, local max, so local min is occurring at x is equal to 1. Local max is occurring at x is equal to 0. That's what the first derivative test would tell us. Does it make sense? Any questions? No questions. Okay. All right, let's keep going. So yeah, so 3 is a little bit trickier. So when we take the derivative, we're going to see that considering it is a little bit trickier. And in fact, this is where like the undefined part is going to matter a little bit. So, okay, taking the derivative, we're going to end up with 6x to the negative 1/3 minus 3. And the normal process we would do is set equal to 0 and solve, which I would plus 3 divided by 6. I would get x to the negative 1/3 is equal to 1/2. And you could then, you would view this guy as a cube root in the denominator, so you would reciprocate, and then you would cube. So that is going to give us x is equal to 8. Right. But if you thought it was just that, then technically you'd be wrong, because there's another critical number here, which is when it's undefined. So the way to see that better is if we actually rewrite this f prime to not involve this negative power. So if we instead write this as a cube root in the denominator, you can see immediately that this guy is undefined for x is equal to 0. I'm trying to think, how do I want to maybe I'll do that. Yeah. So you end up with 2 critical numbers. Critical numbers, x equals 0 and 8. Maybe I can do that in the box. Okay. Right. And so this really plays an important role, because if you didn't get that, then your sign chart would actually be incorrect. Right, so we have 0 here, we have 8 here. And now in order to figure out the intervals, it's a little bit trickier to just think about this without plugging in numbers. So for this, it would totally make sense to just plug in numbers. If we take 1 here, that's going to be 6, so we end up with a positive. If we go over here, actually for this region, I wouldn't pick a specific number, although you could, but the thing is that like the first number that you would pick is like 27, because that's a perfect cube. But yeah, the reason I wouldn't is because 8 over here balances the equation, so it makes this expression equal to 0. And so if you pick a number that is slightly greater than 8, what you know is that then the denominator is going to be greater, so the whole fraction is going to be smaller. The 6 divided by that fraction is going to be smaller, and so you end up with negative. But if you wanted to, you could also pick, well, you could probably pick like a million or something like that, right? You pick a million, then like this thing's really small, and you get -3 mostly. Okay. Now what about to the left of 0? Well, that's also something I need to maybe remark about. So you have to remember that actually taking a cube root of a negative number is perfectly valid. Taking a square root is not valid, but taking a cube root is fine. Like for example, -2, when you cube that, you get -8. Therefore, the cube root of -8 is -2. Right. So if your root is actually an odd root, right? A cube root, a fifth root, seventh root, all these odd ones, they actually extend to the negative side, whereas the even ones do not. And that's just because raising to an even power is never going to give you a negative, or not without complex numbers, which we don't want in calculus. Okay, so yeah. So a negative is fine. And what ends up happening is that the cube root ends up being a negative when you evaluate it. So you end up with a negative fraction here. So you get negative and then -3. So this is negative. So yeah, without that 0, without having 0 as a tick mark, you would get a incorrect sign chart. Your conclusion would be pretty off. Okay, now that we have this though, we can then conclude things using first derivative test, which just means like, look at the neighboring regions of the critical number to read off, like, is it a local min or max? So let's see, local min, local max. So maybe I can draw a sketch on top here as well. decreasing, increasing, decreasing. Okay. And so local min, x equals 0. Local max, x equals 8. Might be better to say add x equals, so maybe I'll just make these add signs. Yeah, I don't think that in the slides I don't think he actually like calculates what the coordinates are. If the problem asks you to, then you probably you should. But for this, I don't think it is asking you to, so I didn't bother to calculate these things. For 3, it's reasonable, but for some of these problems, it's not very reasonable to plug in. Like for number 1, it would be pretty difficult to plug in things, maybe. And wait, not 1. What am I thinking? There was a problem later where it's like doesn't make sense to plug in. I don't know. Okay. Right. So that was 3. Everyone happy so far? Okay. So 4 is tricky in another way. For 4, we actually have an infinite we have actually, well, we have infinitely many critical numbers. So running through the same process like we've been doing, we take the derivative, set equal to 0, and solve. So this is going to give me sine x is equal to cosine of x. And so I want to at least check that people can follow. So give me one value for which sine x equals cosine x. There should be at least one value that comes to mind.
Is it pi?
Not pi, no.
Or 0? 0 and 2 pi?
So actually, if you're dealing with those values, what happens, like for example, just take 0, okay? Cosine of 0 is 1, sine of 0 is 0. So if you're working with angles that correspond to the axes, you're always going to have one of them is 0 and one of them is plus or minus 1. So it's not directly on the axis.
Would it be 45?
45 degrees or pi over 4. Yeah. So pi over 4 is the one that should definitely come to mind. Okay. So just thinking through the trig table, right? I created a trig table for you guys way in the beginning of the semester. Pi over 4, or 45-degree angle, sine and cosine both take the value of root 2 over 2 for that. That's kind of how you should know. Like you can remember like, oh, it's 0, 1/2, root 2 over 2, root 3 over 2, and then 1. That's how sine goes, and then cosine goes in the opposite direction. Just flip the whole thing around. And so they both line up at root 2 over 2 at 45-degree angle. There's one other angle that's a little bit harder to spot here. I don't know if you can tell me. No, nobody? Okay. So the other angle is actually, it's also a 45-degree. It's just, gosh, you guys are using degrees instead of radians. I don't even know if this is it 45, 180? Yeah, it is. Okay, yeah, right. But it's the 45-degree angle in the third quadrant. It's 5 pi over 4. And the thing is that there's an infinite family of both of these because we can wrap around the circle as many times as we want. So we have infinitely many critical numbers, pi over 4 plus 2 pi k, and also 5 pi over 4 plus 2 pi k. Okay. Yeah. So yeah, if you want to actually, I don't know.
Wouldn't that be the same? Couldn't you just do like pi over 4 plus pi k?
I could, but I'm not going to want to do that actually. In this case, breaking it into 2 families is useful because we'll see that actually one of the families is going to correspond to the mins and one of the families is going to correspond to the maxes. So this separation is actually useful in this case. But that's a good point. Yeah. the thing I was gonna say was about these angles. So if you're working in degrees, you better put that degree symbol. Otherwise, I don't know. I would be quite unhappy with it if I see an angle that's supposed to be degrees, but then it doesn't have that, because then I'll just gonna treat it as radians and then mark you wrong on that. You should be working in radians anyway, in a math class. In an engineering class, fine, maybe use degrees, but okay, whatever. Right, so what are we doing here? Local mins and maxes. So to do this, I'm gonna need to draw a fairly big number line just to have enough repetitions to be convincing. Okay, so I'm gonna put the pi over 4, and I'm gonna put the 5 pi over 4. But then I'm also gonna wrap around the circle a little bit. So I'm going to put in the next value. So if this guy corresponds to 5, then the next is 7, the next is 9. 9 pi over 4. And I'm also gonna want to go backwards. So we start at pi over 4 and then we go backwards. We get negative pi over 4 and negative 3 pi over 4. Okay, and with this many, it should be more convincing. Okay, so now we pick values. So we need a value. Yeah, here basically we just need to pick values because it's not that possible to analyze the behavior of the derivative function. Right. So we want to pick a value between negative 3 pi over 4 and pi over 4 and plug that into h prime. Well, a decent value would be 0. So we plug 0 into my derivative function. So cosine is going to give me 1, sine is going to give me 0. So I get a positive value. And then between pi over 4 and 5 pi over 4, so what I'm doing is I'm looking at the circle and just picking a nice number to use, a nice angle to use. And pi looks like a nice angle to use. So I'm going to plug pi in. And in that case, cosine of pi is going to be -1. Sine of pi is going to be 0. So I get a negative. And then for between 5 pi over 4 and 9 pi over 4, again, I pick another nice number along this arc. Maybe my cursor is hard to see, but this arc. And so 2 pi is a nice number, which is actually the same thing as 0. But yeah, if I plug h prime of 2 pi in, I'm going to get 1 minus 0 as before, so I'm going to get plus. And you should be able to like basically see the pattern here that this thing is going to keep oscillating. It's going to keep going from plus to minus to plus to minus and kind of extends it finally. And so that's and then maybe what I'll do is I'll use some colors here to denote things. So this angle and this angle are the same or equivalent, and this angle are equivalent. And you see, like with the ones that are red, you're going from plus to minus. The ones that are blue, you're going from minus to plus. So that shows you that the families are actually splitting up into the local mins and local maxes. So local mins, local maxes. Let's see, the mins are which ones? The 5 pi over 4 plus 2 pi k, and the local maxes are where x is pi over 4 plus 2 pi k. Did I label this wrong? Oh, hold on a sec. Let me just. Okay. I think I just mixed up words when I was doing this on paper. So I hope I didn't mess it up the other class. Well, let me. If I mess it up, they should catch it, right? This is a very easy mistake. If I made, stare at it one more time. How did I have no idea. Weird. Okay. All right. So hopefully you guys are okay with that. And then the next thing is this thing about globals, global mins and maxes. So if you have some intuition about this, you might conclude, and the conclusion is correct, but concluding it direct from intuition is maybe a bit iffy. You'd conclude that like maybe these local mins and maxes are all global mins and maxes. For this function, that is the case, okay? But if we want to reason about this more carefully, you actually do need to like do a little bit of argument about plugging things in. I'll say the reason why is because like, so in this function, let me get cursor again, sine plus cosine, okay? So if you were to mix and match your sines and cosines, you could do this in a number of ways. You can like add some extra sines and cosines that have like a different oscillation, like make it like 3x instead of x, and you maybe scale one of them up or down, like put a little amplitude on top of it. Then what you can do is you end up getting like a repeating function, a periodic. We call this periodic because it keeps repeating. A kind of function like that that repeats infinitely, but that has local mins and maxes that aren't globals. Here, things work out so nicely that the locals are the globals, but that doesn't have to be the case. You can easily construct a counterexample to that. So what we really want to do is we want to be able to say, like, if we plug in for like all of the things in the family, they'll give us the same value. And that's actually pretty easy to see. So what we do is we want to plug in to the function, the original function h, the whole family of values, and see that they'll give us the same number. Well, they indeed will, because 2 pi k, when we just look at this h, sine and cosine are periodic with a period of 2 pi. So it doesn't matter if you're tacking on a 2 pi or not. That doesn't change the value of the function, or the output that sine will give you, the output that cosine will give you. They'll give you back the same number. So yeah. So this actually just reduces to just plugging 5 pi over 4 in, which is negative and negative. Yeah. So yeah, this is again like a 45-degree angle. It's pi over 4, and so you're going to get a root 2 over 2. But in this third quadrant, you get a negative root 2 over 2. And sine plus cosine means you get 2 copies of that. So we just get a negative root 2 in total. Then for the other family, you should also write something about that down. 2 pi k. Well, again, the repetition of 2 pi can be gotten rid of. So it just reduces to h of pi over 4. And that's going to be root 2 over 2 plus another copy. And so you just get root 2. Okay, so on all of these local mins, you attain the same value, which means that that is actually a global min, and same thing with the maxes. So I'll just copy it again. Global, maybe I'll say yes. Global mins at x is 5 pi over 4 plus 2 pi k, and global maxes at x is equal to pi over 4 plus 2 pi k. Yeah. So yeah, if you're not convinced about this whole sine cosine argument, like, it's a good idea to just play around with the graphing calculator, and you'll experience firsthand like what happens with these different things. You can just adjust things around, and that's kind of actually the beginning of a theory called Fourier analysis, which is very useful if you're an engineer, which I'm guessing at least one person is, since he has like degrees. Yeah. Okay. Right. So we're a little short on time. I'm gonna have to go a little bit faster. Number 6. I want to get 6 done just because I got it done the previous time, and we'll probably have enough for the next class to go over. Like, well, to use most of the time for the next class. All right. So 5 is actually very straightforward. 5, you just read the problem and you understand what it's saying. So the population is increasing. That tells you something about the first derivative. So that tells you that the first derivative is increasing, is greater than 0. So therefore, I'm talking about plus. The rate of population growth is slowing. So that statement you have to kind of untangle a little bit. Population growth is actually the first derivative, where you have population, then you have the population's growth, and then you're saying the rate of population growth is slowing. The rate of population growth is actually the derivative on top of the derivative, aka the second derivative. And it's slowing, meaning that it's negative. And so, yeah. And you could also say like that's concavity. I don't know why we're not talking so much about concavity yet. Okay. You sort of use it in the next page, which we'll get to next time. Okay. So 6. 6 is kind of terrible because of this fraction. Our function requires us to use quotient. So critical numbers, again, take the derivative, set it equal to 0, and solve. So when we take the derivative, we're going to have x plus 1 e to the x minus e to the x times 1 over x plus 1 squared, which we would try to simplify this just a little before we can actually set equal to 0 and solve. So I can pull an e to the x out, and then I'll have an x plus 1 minus 1. So I'll have an x over x plus 1 quantity squared, and we would want to set that guy equal to 0. Or we would have it be undefined, which actually turns out to give us another value. So but first, x equals 0. So one thing to note is that this e to the x is never going to equal 0. It's always positive. So that 0 can only come from this factor x here. So x must be 0. For undefined, well, we need the denominator equal 0, which is possible here because we just let x be minus 1 and the denominator is 0. So both of these are critical numbers. Maybe I can just box these since they're nicely aligned. Okay, now the first derivative test to find that. Yeah, so apply the first derivative test. That means we need a sign chart. Minus 1 and 0. And now we stare at this function. This e to the x times x over x plus 1 quantity squared. Okay, well, the way I would think about this is e to the x is always positive, so I can kind of ignore that. And also this x plus 1 squared is always positive, or 0, but we've already included that for consideration. So it's always positive, so we can also exclude that. So actually the only thing that's going to contribute a change in sign is the x. So that tells us we start off on the right-hand side, we end up with plus, and when we switch over the 0, we end up with minus, and this is also going to be minus, because the only sign change that will show any change is going to be the one corresponding to the x, which is the 0. Okay, so I guess one remark I can make, like, is this x plus 1 quantity squared? If that wasn't a squared, if that was a cubed, a fifth, any odd power, then that would contribute a sign change. Jumping over this minus 1 would actually flip the sign of the whole g prime. But because it's an even power, jumping over the minus 1 does not change the sign. Because the sign difference gets squared away. All right, so now we have the sign chart for g prime. And if you weren't comfortable with that process, you would have to probably just like pick values and imagine plugging them into the function and seeing like, oh, your function is positive, or oh, it's negative. So you would end up with those numbers. Either way, you would get this sign chart. Okay, so now we can say something about local mins and maxes. Let's see, this one is just a local min. So at x equals 0, so there are no local maxes, and there's a local min at x equals 0. Good. Okay. So that was us applying the first derivative test. Now it asks us to apply the second derivative test, and then later it asks us to compare. So this second derivative test is the part that's a little bit more time consuming, I would say. But what I'm gonna do is I'll probably end up just skipping some of the algebra, a little bit of the algebra. Oh, come on, let's go there. Okay, something weird is happening to my computer. Okay, I need to hold on a second. All right, seems like it's working now. All my windows disappeared. All right. Yeah, so second derivative test. G double prime of x. So I need to take the derivative of the first derivative. That's going to involve a product rule inside of a quotient rule, which we have to do. X plus 1 squared. Derivative of x e to the x is going to be e to the x plus x e to the x, and then minus x e to the x times a 2, I don't need that big parenthesis, times a 2x plus 1 all over x plus 1 to the fourth. One simplification I can do is I see that there's an x plus 1 in common everywhere, so I can just get rid of one copy of that. But then from this point, so we have to recall, like, what is the second derivative test about? It's about taking your critical number, or taking critical numbers that correspond to setting the first derivative equal to 0. So in that case, it's only going to the only critical number that we can use is the x equals 0. So we would use that, and we would plug that value into the second derivative. Second derivative test uses requires us to plug into the second derivative. So we could plug into the second derivative at this stage. It's just going to be a little messy. I guess you could do that though. But what I did on paper, at least, was I actually simplified this completely. So the way you do that is you start with this e to the x plus x e to the x. You notice you can factor an e to the x out, and then that's going to combine with x plus 1. You'll have 2 copies of x plus 1, and then you can factor the other e to the x out, and you can simplify it a little bit. Either way, you'll end up with this. And in some problems, it will be necessary to actually deal with us taking that second derivative and setting that equal to 0. But that's when we're dealing with points of inflection, or when we're trying to find like points of inflection, when we're trying to like do the concavity and everything. I think maybe that'll be like next week, perhaps. But yeah, for this second derivative test, that does not require that. Instead, we're taking the critical points, we're plugging them into the second derivative. But with this function, it's easier. So I just need to plug 0 into the function, and I end up with 1 times 1 over 1. And the key point is that this is positive, which means that we get that that the situation is concave up, which means that what we have is a local min. Okay. And I'll specify this is a local min at x is equal to 0, right? So this second derivative test applied to x equals 0 tells us that that is a local min. You can imagine, like, if you had other critical points that you could use, you could then also plug those other critical points into the second derivative. It's just that this function was a bit too simplistic and it only had like this one critical point. You could easily make a harder problem that has multiple, right? So, and lastly, D, right? Which test do we prefer? So I think that the consensus should be that the first one is the better one to use in this case. It's just easier to not have to take that second derivative and plug into it, right? For the first one, yeah, I had to take one derivative, but then I could just from there calculate it, as opposed to taking 2 derivatives, the second one being a little bit more nasty. There's one step of algebra. If you're clever about things, you can do the mental arithmetic. There's only one step that I skipped here, technically, but if you have to write a few things off to the side, then it's a few algebra steps. So the first derivative test would have used less work than the second. All right. Okay, so I'll stop here. Are there any questions or final remarks? No? Okay, then I'll see you guys next time.